Hi, and welcome to this third episode of doing a PhD in 5 minutes. Well, it'll be a little bit longer than that, but it's an experiment. What we have here is LiDAR data from 2022. It's very accurate. I'll show you how accurate it is in a minute. This is the fort, Roman fort here, Piercebridge. Here you have Deer Street, and the red dots are mills. So here we have one mill, and it's fed by this stream or beck, and I presume there was a dam here to collect the water in this area. There's information about a beck feeding a mill on here, or this mill here. I presume there was a dam here, and they were collecting the water up here, in this area. This mill was fed through this watercourse, it's man-made watercourse, and there are some papers that say this was feeding a water mill, but I'll get to that a bit later. So here we have the area which was excavated in the 1970s, which is said to be part of a bridge. So I'll have a closer look at that. Here you can see what they call the abutment for the bridge. I'll just put contours on. These are at 200 millimeters, these contours. So here we have a photograph of this area. It's in the 1970s. You can see what a mess it was down there. That was probably caused by the dragline excavation when they were excavating the gravel. Here we actually have a level. It's from the 1999 paper by Scott and Fitzpatrick. So there's a level there at this point of 52.7. So go here. So over here you have the level, and we have 52.77, 75 again. And this paper says 52.7. They only go to one decimal place, so that's accurate enough. They also talk about a faint line in stone. So this is this point here again, the abutment. There's a faint line there. But this is quite important. This is for level, so I presume this was all level, and not like that. Okay. Right. So if we take off the actually we take this out first. Take off the contours. Zoom out again. You see there's a line there. Looks like that could be a canal, but there's definitely something else happening up here. See, you've got faint lines here, which was probably where the river ran in the past, in the distant past. You can clearly see this line here and this one here. If we actually look at this one a bit closer, that's in the north. See, it's quite large. When I was looking at this, I was wondering why it went so far up there, because you could put a dam across here, and then you just need to come through here, for example. But this is pretty large, and this is quite large. So I actually had a look and to see what the elevation was like. And it's massive. This piece here, where I thought the canal would be going, it's huge. It's measuring 24 meters there, and 47 meters there. So that's 23 meters across. And if I actually do a line from there to there, you can actually see it's the same level as the river. In fact, it actually goes below the level of the river. So I estimated there was something like between 3 and 5,000 cubic meters of something coming out of here. And this combined, it may even be more. And being next to a river, which has actually changed over time, you'd say that most likely material that came out of there was clay. It might be rock, because you can see it's quite starts to go quite steep there. But I would say it's probably clay. And one of the main components in building a dam is clay. Although, if you're building a bypass canal, you're going to have material coming out. So for here example, let's do the measurement on that. That's 270 meters. Calculated, you'd have about 1,000 cubic meters, over 1,000 cubic meters of material coming out of there, which could be clay, and that's after taking off the topsoil. Right. Okay. So if we go to this is a PhD done by James D. Anderson. The Piercebridge formula in the northeast of England, an assessment and alternative method of supply to the Roman army. If he'd actually gone looking for answers, he might have done a decent PhD, but he didn't really go looking for answers at all. I'll get to that later. In his PhD, page 72, he's talking, this bit is about this piece here. Rather than for navigation, Coupland argues that the bypass canal was cut in the first place as a medieval mill race. Okay, so this is a medieval mill race, except it's 270 meters long, it's about 4 meters wide, and it's at least 2 meters above the river level. So I'll just show you that. So here we have 50.56, 52.86. So yeah, it could go up a bit further here, but it's still going to be 2 meters above the river level. That's pretty high. If we go down here and look at this one, so we have 53.79, 54.7. So you have 1 meter of difference here. So that may not sound like much, 1 meter difference, but it's actually 4 times the amount of material to build this than this. See if we can find. Here we go. So this is probably what was used in the Roman period to actually calculating the size of a dam. Once they'd modelled, so let's say they model a 2 meter dam, they figure out how much material they need for a 2 meter dam. From that, you can use this to actually calculate a 4 meter dam or a 1 meter dam. Because basically, if you half the size of the dam, you reduce the quantity of material. Well, you divide it by 4, so it's 1/4 the amount of material. So I can't understand why you'd build a dam here, because you need to go 2 meters high, and then here you could build a dam and you only need to go 1 meter high, and it's 1/4 the amount of material. That doesn't make sense. And you have mills over here, this one for example. All you have to do for this is just build a dam here, you know. It's a watercourse. There's no digging. You don't have to dig out 1,000 cubic meters of earth, plus actually it's probably nearer 1,500 meters of earth. You don't need to dig it out. This one, fed by the beck from here. You don't need to dig it out. All you need to do is to do a dam. So the economics of this being a mill race in the Middle Ages doesn't add up at all. You've got a huge volume to take out, plus you've got this massive dam which is 4 times bigger than the one just up the way. The only way this works, if it was used, is to actually reuse an existing structure, which would be a dam here. So that's that. Okay, if we go back to this, one thing that occurred to me was this probably isn't a normal dam. It's next to Deer Street. It's a major highway. You've got a fort here, and this may be just for prestige, building such a big dam here, because there has to be a sweet spot with regards to heights of dams, because instead of building say a 4-meter dam here, you could build two 2-meter dams, and you'd use only half the amount of materials. The canal length would be the same, and if you're using flash locks, you'd have the same number of flash locks. So to be easier to build, there'd be less problems because you're not going so high, less trouble with the water flow of the river. You can do it much quicker, and yeah, it's just something that you'd think they'd actually do, is to actually look at what is the most favourable height to be building along the river. And not every river is going to be the same. It'll change depending on the gradient of the river, but this is probably what they actually use for calculating that. And I don't see any reference to that in the archaeological material in relation to Piercebridge. No one has bothered to even look at that. So here we have more of James Anderson's PhD about the position of the bridge. The big problem for me with regards to this being the location of the bridge, and what archaeologists have tried to argue, is that there is absolutely no reason for this to move, because some of the structure is still there, and there's absolutely nothing of this left. So I'm pretty sure this was a very sound structure. And the river moving, no, I don't think so, because there's a massive amount of Roman material found here. And what are they going to say? That it was actually this level was actually a lot higher 500 years ago, and it cut down in the last 500 years to make this a viable option? No, I don't think so. So river moving sideways and down, I don't think so. Okay, so I'll finish there, and in the next episode I'll look in more detail at one specific part of James Anderson's PhD to show what is really wrong with it. Okay, thank you.